Here it is, the last lesson of Physics 20, and it's all about sound and sound waves. So get ready for me to make a lot of funny noises in this video. Yeah, it's going to be super exciting. All right, so before we do that, let's go, of course, over speed of waves, because of course, depending on what kind of medium you're in, waves will go different speeds. And of course, depending on what the wave is, but no, actually, I'm pretty sure all waves travel differently through different mediums. I could be wrong, but I'm pretty sure. So it is determined by medium. So for example, sound waves travel differently through water than they do through air. They travel slower. So it actually depends on the elasticity and the density of the substance that you're going through, okay, or that the wave is going through, okay? But I'm not going to go over that too much more. Just know that the speed of a wave is different through different mediums. And even the speed of sound, even if it's going through air, it can even change with the temperature of the air, which is kind of crazy. So on a really cold day, speed of sound actually is slower than on a hot day. So if somebody's yelling at you from across, I don't know, the yard or something on a cold day and you can't hear them, maybe it's because they actually need to yell a little bit louder, because you actually just will not be able to hear them as well, or the sound won't get to your ears as fast, okay? So, yeah, that's a crazy thing. So speed of sound is actually affected by the temperature. So if there's a higher temperature, then we have faster waves and sound gets to your ears faster. So that's how we figure this out. You don't need to know that. I just think it's interesting. Maybe you do need to know it. I don't know. But do you need to know it for like a Physics 20 test? No, probably not. But I mean, if I gave it to you on a test and was like, here's the temperature, should you be able to find the velocity? Yeah, you should, because it's just like T, and that's in degrees Celsius. Okay, so if you use that equation, you can find the speed of sound in any temperature, degrees Celsius, right? So let's actually take a look. What would be the speed of sound on a hot day versus a cold day? Okay, so hot day, let's say it's 30 degrees Celsius. Right? That's a pretty hot day for us. I know that's usually when I start to get annoyed with hot weather, when it gets 30 or more. So that's a pretty hot day for us. So what do we get if it's 30 degrees outside? What's the speed? It is 349 meters per second. So that's how fast sound is traveling. And so let's compare that to a cold day. How fast is speed traveling on a cold day? So let's say, I don't know, what's a cold day? Minus 30? We did 30, so let's do minus 30 degrees Celsius. Might as well. Okay, so if we calculate that, we get 313 meters per second. That's a huge difference. That is 36 meters per second difference, which that's fast. So there you go. On a hot day, if you can hear stuff really fast, there you go. And on a cold day, if it takes sound a lot longer to reach you, at which point it's been dissipated more and you can't hear as well, there's an actual reason for that. So I think that's pretty cool. All right, let's keep going on to sound and its characteristics. So there's a really cool characteristics about sound that if you have two tuning forks, or really two things that are vibrating within 7 hertz of each other, right? So hertz is what tells us the pitch of a sound. And so 7 hertz isn't that different. So they're almost exactly the same pitch, but they're just a little off. So if you know anything about music, it's basically like if you had a note and then that same note, but it's just a teensy bit flat or a teensy bit sharp. And if you have just those two things, like tuning forks like that vibrating at the same time, they make this thing that's called beats. What the heck does that mean? It's like this wow, 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 wow sound, okay? So that's just something neat that happens. And it's just because it's like interfering because the sound waves are so similar, but they're just like this tiny bit off. They really mess with each other. Okay. And the number of beats that you'd get like per second would be the second frequency minus the first. Okay. So I just think that's pretty cool. Another characteristic of sound is when you get shock waves, and that's when an object travels faster than the speed of sound. So of course, when they started making airplanes that go faster than the speed of sound, they saw shock waves in the air, which is pretty crazy. I don't know, I've never seen them, but that's a thing that happens. Things that are a little bit easier to explain, and of course that we know because we're just like always listening to sound. Pitch is of course how high or low sound is. So right now, the pitch of my voice is changing a little bit because I go up and down, like not a lot, but a little bit, because if I didn't, then I would be really monotone. It would just sound like this all the time, and it would be really boring. So pitch is just, again, how high or low you go. So the higher your pitch is, when you talk really, really high, then you have a really high frequency. And then if I talk really, really low, I have a really low frequency. Okay, so high frequency means a smaller wavelength. So a higher pitch means a smaller wavelength. So it just means the wavelength would be like this, rather than with a lower pitch, it would be, might be a little bit exaggerated, but that's definitely a higher pitch versus a lower pitch, okay? Because if sound is going at the same speed, then we know if the frequency goes up, the wavelength goes down, and if the wavelength or frequency goes down, the wavelength goes up, okay? So pitch refers to how high or low sound is, and of course, the higher the frequency, the higher the pitch. The lower the frequency, the lower the pitch. Loudness is determined by intensity per unit area. Okay, or energy per unit area. And it's measured in decibels. Actually, like the unit measure is actually a bell, but a bell is too big, so we use decibels, right? Because that's like a tenth less. So another way you can think of loudness is amplitude. We already know a little bit about amplitude, right? I can have a wave with this kind of amplitude here. If I'm thinking about a sound wave and I want a louder sound, but I want it to still have the same sound, then I need to keep the same pitch and stuff. So I can't change the frequency, which means I can't change the wavelength, but I can change the amplitude. Right? So I'm still keeping the same frequency and the same wavelength, but I'm making a bigger amplitude. And that's what's actually going to get you a louder sound. Now, you may have noticed that, like sound doesn't travel in a transverse wave. We still use transverse waves to explain it a lot just because they're easier to draw than non-transverse waves. But these peaks and valleys refer to when we have lots together and then some apart, and then of course a peak would be lots together and then apart, and then lots of air particles together, because that's all it is. It's just air particles moving across air, and that is how we get amplitude. So if you have a small amplitude, it just means it's affecting less air particles. Okay, so if I want to up the amplitude, I just need to make it affect more air particles, and then I'll have more volume. So that's what you're going to do. So you just want more air particles affected, and then that's how you get more volume. Okay? So that's actually what's going on, but it's just not as fun to draw. But that's how you determine how loud something is you make the amplitude of the wave bigger, and then we measured it in bells, which is energy per unit area. Okay? So let's go over a really cool thing about sound, and a really cool thing that happens with sound that you guys have probably heard of before. And there's a popular TV show that, for all intents and purposes, I don't really like, but this is a really good example of what the Doppler effect is. And if you've seen it, if I just go meow, that's the Doppler effect. But basically, It's a change in frequency due to relative motion of source and detector. So if something is making a loud sound and it's moving across you really, really fast, it sounds like when it's coming towards you, it sounds like it's getting higher. And then when it's going away from you, it sounds like it's getting lower. So just like a really fast car, if it's coming towards you, it sounds like it's going, and if it's going away from you, it's going, I told you I'm going to make a lot of fun noises in this video. So there you go. That's all the Doppler effect is. Now, why is that? Why does it make a higher sound as it comes toward you and lower as it goes away from you? The reason is because, well, if something's at rest, right? So here's a car and it's like on honking the horn and it's just not moving at all. Then of course the horn isn't going to sound like different pitches. It's just going to be like one blaring long honk at the exact same pitch the whole time. But if you move that car that is honking its horn, then it's going to do that thing where it goes, right? I told you, lots of fun sounds. So the reason is because when it's moving towards you, the sound waves are kind of like pushing into themselves. Okay, so these circles represent the sound waves. And then when it's moving away from you, they're like spreading out more because the sound is moving away from itself as it leaves its sound waves behind it. Okay, and that is exactly why it does that. So of course, since the sound waves are running into themselves as they're coming towards you, that's going to give us a shorter wave, which guess what, is a higher pitch, because lower wave means higher frequency, means higher pitch. And then when it's going away from you, these waves are spreading out more and more because, of course, the source that's making the noise is moving away from where your ears are picking up on the noise. And so those sound waves are spreading out, which means we have a higher wavelength, which means we have a lower frequency, which means we have a lower pitch. And that is the Doppler effect. Okay? So if something's moving towards you, smaller wavelengths, higher frequency, higher pitch, okay? So it's higher pitch over here. And then, of course, if it's moving away from you, then the wavelengths are spreading out, so they're longer, and therefore there's a lower frequency, and that means that we have a lower pitch. And there you go. So that's something that's important to know. If it's moving towards you, wavelength goes down, frequency goes up, pitch goes up. If it's moving away from you, the wavelength goes up, the frequency goes down, and so you get a lower pitch. At no point is sound moving at a different speed, because it's not like the temperature is different in front of the vehicle and behind the vehicle. No, you're standing in one place, the temperature is the same, and we know that's what affects speed of sound, so it has nothing to do with that. Speed of sound is constant, so if speed of sound is constant, then the wavelength and frequency are inversely proportional, and therefore as one goes up, the other must go down at the same rate. Okay, so that's that. So we do have an equation that helps us calculate what frequency you hear based on whether something's coming towards you or away from you. Okay, so F, this little thingy, this little tick thingy, we can call it prime. So F prime, or whatever you want to say, that's the frequency that you hear, okay? Whereas this F is the frequency of the actual source. So F just needs to be, what's the frequency of the source? Because remember, the frequency of the source is not changing. If somebody's driving past you with their horn on, the frequency of the horn is not changing. It's not like the pitch is going up or down. And if you sit still and listen to a car's horn, you realize that, right? So that's the frequency of the source, but this just needs to be, what's the frequency that you hear? So obviously that's going to be different depending on whether they're coming towards you or away from you, okay? V this guy, those guys are the speed of the wave, okay? And then we have V naught, which is the speed of the observer. Usually that's 0, okay? But it's there just in case it's not 0. But usually, often we look at an observer who's not moving. And then Vs is the speed of the source. So for example, or in the example of a car moving towards you and you're the observer who's standing still, then your speed is 0, and then Vs is just whatever the speed of the car is coming towards you. Okay? So you do have this equation on your data sheet. It's just, you just don't have this. Okay? So if you're ever expected to use that part on a test, I'll give that to you. Okay, and if not, then you can just use the equation on your data sheet. Okay, now you might notice we have plus or minus here and minus or plus here. So you're like, what's that all about? Well, the signs changed based on whether something's moving towards or away from you, and you need to know which signs to use if something's moving towards you or moving away from you. Okay, so if something's moving towards you, you need to use the top sign. So what does that mean? It means that these signs, this plus and this minus, are what you use if something is moving towards you. Which I'm sure that means you can guess that you'd use the bottom signs, the minus there and the plus in the denominator, if something is moving away. So if you're somebody who just likes to memorize things, you can. But of course, in physics, it's better to know the reasoning behind it. So think about it. If something's moving towards you, what's happening to the frequency again? It's going up. So that means I need a bigger numerator than my denominator. So therefore, I should add in my numerator, subtract in my denominator, so I'm dividing by a smaller number. Okay? But of course, if something is moving away, you'd use the bottom signs. So you want a small numerator and a big denominator because, of course, that's going to be a lower frequency. Okay, so I want to divide by a bigger number. So remember, means there's a higher f prime, which is the frequency you'll hear, and this would be a lower f prime. So if you're bad at memorizing stuff, like me, you can always reason it out, saying, okay, I need a higher frequency than the original. So if I add in the numerator and subtract in the denominator, I'll get a number bigger than 1 in here, and then I'll be multiplying this f by a number bigger than 1. Good. If I know that I'm going to be hearing a lower frequency, I need a number that's lower than 1 with the whole fraction. So I'm going to subtract in the numerator and add in the denominator so that I can get a smaller numerator than I have denominator, and I have a number that's less than 1. Okay? So reasoning stuff out is really good for you. It's a really good thing to be able to do. So I think you should be able to do that. So just keep in mind the signs are given like this, like it says plus or minus on the top and then minus or plus on the bottom, just telling you always have to do the opposite thing in the numerator than in the denominator. Okay? But then of course on your unit or on your data sheet, you're not even given this. So it just says V over minus or plus or minus V plus VS. Okay, or V plus or minus VS. So you just need to know when to use plus, when to use minus in the denominator. Okay, so that's that. So let's do one example, and then that's it for the whole course. Like Physics 20 after this, you have all the information. Congratulations. So here is our example. We have an ambulance emitting a sound of 500 hertz. So there we go. That is the frequency of the source. It's heading towards a stationary observer, so that means that the velocity of the observer is 0. If they hear a pitch of 520 hertz, so this is weird. So if I go back here, I notice, so it gave me the frequency that I hear, that's f prime, and it gave me the frequencies. I must be finding something inside the fraction. So that'll be fun. So let's go over that again. So if they hear the pitch of 520, which is a higher pitch, Okay, so is it moving away or towards? We're going to determine how fast the ambulance is traveling. Assume the speed of sound is 340 meters per second. Okay, so we know our original frequency is 500 hertz, and we know the frequency that we're hearing is 520 hertz. So is this moving away or towards? That's the first really important question you got to answer yourself. Higher pitch means it's moving towards. Moving towards. Okay, so what does that mean? It means I need a big numerator and small denominator. So I have to add on the top and subtract on the bottom. Okay, so if I use the equation that your data sheet gives, again, they don't even have speed of the observer. So it's just speed of sound plus or minus velocity of the sound or the source. So again, which one am I going to use here? Well, it's moving towards. I'm going to have a higher frequency, so I need the smaller denominator, so I need to subtract in the denominator. Okay, so I'm going to use subtraction when I'm looking for the speed of the source, which is, of course, the ambulance. So doesn't rearranging this equation look fun to you? Well, first step, what are you going to do? You're going to divide both sides by f, okay? So I get f prime, frequency heard, divided by the frequency is equal to v, divided by v minus the velocity of the source. Now I've given you a little trick for when you have two fractions equal to each other and need to solve for something in the denominator. And remember that if you flip both the fractions, then this equal sign is still okay. So you can trust that equal sign. It's okay. It's not trying to mess you up or anything like that, because I flipped both of the fractions. Okay, so of course I'm going to multiply both sides by v, and then I'm going to, here, I'll just show you. So I'll multiply this side by v. Okay, I get v minus the velocity of the source. Of course, I'm looking for the velocity of the source. So technically, I'm going to add that to both sides and subtract fv over f prime from both sides. So what do I get? I get the velocity of the source as the velocity or the speed of sound minus, sorry, not the velocity of the source, the speed of the source. We don't care about vectors here. So it's the speed of sound minus the frequency times the speed of sound divided by the frequency heard. Okay, so let's see. So again, the speed of sound was 340 meters per second minus the frequency of the ambulance was 500 hertz. Okay, again, speed of sound, 340 meters per second. Divide that by the frequency heard, which was 520 hertz. Okay, and we can get our speed of the source as, I don't know, because I haven't calculated that ahead of time. So just give me a minute. And that gets us 13.1. Do we need, yeah, we need 3. This is 13.1 meters per second. Okay, there we go. There's the speed of the source of the ambulance, 13.1 meters per second. So it's actually not going that fast. So this ambulance needs to pick it up. Anyways, that is it. That's the Doppler effect, which I think is a fun way to end Physics 20. So hope you enjoyed it as much as I did. I mean, I always enjoy physics, but I'm crazy like that. Anyways, thanks for watching. Hopefully I'll see you in Physics 30. Goodbye.